Okay, hi everyone. This will be part 1 of my video series on general chemistry, and this video will cover an introduction to atoms and the periodic table. Let's go ahead and begin by discussing atoms. Atoms are the fundamental building blocks for everything in the universe. This was a concept that wasn't very intuitive to me when I first learned this, but it's true. Everything in the universe can be broken down into atoms. The human body, the food we eat, and the air we breathe are all made of atoms at a fundamental level. And atoms are extremely small and can only be visualized with special microscopes. We are going to look at the structure of atoms and break down what atoms themselves are made of. Atoms are made of 3 smaller particles: protons, neutrons, and electrons. Protons have a positive charge. Neutrons have a neutral charge. And electrons have a negative charge. And it's important to keep in mind that positive and negative charges are attracted to each other, so protons and electrons are electrically attracted to each other. Protons and neutrons are found in the nucleus of an atom. And electrons orbit the nucleus of the atom. The other important distinction is that protons and neutrons have a mass of 1 AMU, or atomic mass unit, whereas electrons have negligible mass, meaning they have basically 0 mass. Now let's take all of this and turn it into a more practical drawing of an atom. So here's an initial drawing of an atom to represent what we just learned. This would be the nucleus. Here's our positively charged protons. Here's a neutral charged neutron. And over here, these would be electrons orbiting the nucleus. These have a negative charge and negligible mass. And we often represent electrons with this symbol here, an E-. And the electrons occupy the orbit of the atom, which is the space outside of the nucleus. The difference between the different atoms is their relative number of protons, neutrons, and electrons. Here's an important point to know. For a neutral atom, the number of electrons always matches the number of protons. If the number of protons and the number of electrons are the same, the positive charge from the protons cancels out with the negative charge from the electrons, and the overall charge of the atom is neutral. Now that we have the foundations of atomic structure, let's move into talking about the periodic table. So the periodic table is a highly organized list of the different atoms in the universe. As we move forward, I would recommend having a larger periodic table in front of you to follow along with. And the periodic table represents neutral atoms, meaning the number of protons matches the number of electrons. Let's begin by talking about how the layout of the periodic table relates to the placement of electrons within the orbit of an atom. So each row of the periodic table represents a different shell. The first row is the first shell, and since there are 2 atoms within that row, that means that shell holds 2 electrons. The next row has 8 atoms, which means the second shell holds 8 electrons. The next shell, same thing, it has 8 atoms, which means the third shell holds 8 electrons once again. Within each shell, going left to right, we add 1 new electron as we progress from left to right. Using all those bits of information we just learned, let's pick an atom and draw a diagram to represent the number of electrons, protons, and neutrons it has. And let's pick nitrogen as our example. So let's start by writing a P here and an N here. And later on, we will write in the number of protons here and neutrons here. But let's start with the number of electrons. So because nitrogen is located in the second row of the periodic table, that means the first shell, represented by the first row, is full. And so we will represent the first shell with a circle here, and it holds 2 electrons, 1 and 2. And then we will draw a second shell, and we will add in electrons to the second shell based on the second row of the periodic table. So we have 1, 2, 3, 4, and then nitrogen is the 5th atom within the second row. So we will add in 5 electrons to the second shell. 1, 2, 3, 4, 5. And so altogether we have 7 electrons. And now let's switch to the protons and neutrons. And so remember I said earlier that the number of protons and electrons are equal for a neutral atom. And the periodic table represents neutral atoms, so we can say that the number of electrons is equal to the number of protons, which means we have 7 protons. But then how do we find the number of neutrons? Well, to do that, let's look closer at nitrogen here. So nitrogen, you'll notice there is a 7 above, and there is a 14 below. If you look at the space for nitrogen on the periodic table, and again, I would recommend having a larger periodic table to work with. So this number up here is the atomic number, and this number here is the atomic mass. And the atomic number represents the number of protons, and the atomic mass is the sum of the number of protons and neutrons. And the units for all of these values would be in atomic mass units, or AMU. So let's use the numbers we know in this equation. We know the atomic mass is 14, and that equals the number of protons, which is also the atomic number, and that is 7, plus the number of neutrons. So with simple math, we can say that the number of neutrons must be 7 to make this equation work. So that is a very handy equation to know, is the atomic mass equals the number of protons, or we could say the atomic number, plus the number of neutrons. Let's go ahead and do another example. This time let's do element number 16, which is sulfur. Let's start with the number of electrons. So the top row representing the first shell is going to be completely filled because sulfur is on a row further down. So the first row is filled, and that holds 2 electrons in the first shell. The second shell is also going to be filled because sulfur is on the next row down. So we have a filled second shell, which is represented by the second row on the periodic table. That's going to give us 8 electrons in that second shell. And then within the third shell, we have 1, 2, 3, 4, 5, 6 electrons. Overall, we have 16 electrons. Notice how the atomic number of sulfur is also 16. So the atomic number really is telling us both the number of protons and electrons in the neutral atom, because those numbers should be the same for a neutral atom. So we can say we have 16 protons. And then for the number of neutrons, we need to go back to our previous equation. Atomic mass equals protons plus neutrons. So the atomic mass of sulfur is 32. So 32 equals 16 plus neutrons. And we can see that the number of neutrons must be 16 to make this equation work. So we can say we have 16 neutrons in the sulfur atom. Next, I would like to define an important term. Valence electrons are the electrons within the outermost shell of an atom. So for our example, the third shell is the outermost shell, and it has 6 electrons. Therefore, sulfur has 6 valence electrons. Valence electrons are very important in chemistry because at the end of the day, chemistry is all about these valence shells and valence electrons. And we will get more into that as we progress through the series, but for now just be familiar with the term valence electrons. Let's quickly review some important trends we've learned so far. So each row of the periodic table represents a new shell for electrons to occupy. And then as we move from left to right within a row, we are adding a new electron. A horizontal row is sometimes called a period. And then columns are sometimes called groups. Atoms within the same group tend to have similar chemical properties because they have the same number of valence electrons. We can divide the periodic table into sections based on which elements are considered metals and which are considered nonmetals. In blue here, we have the nonmetals. And over here on the left, we have the metals. And we can draw a staircase-shaped line over here that divides the metals from the nonmetals. But you'll notice some of the elements that border this staircase are colored in green, and that is because they are metalloids. So metalloids are sort of the in-between between metals and nonmetals, as in they have properties of both metals and nonmetals. Another thing to point out is that hydrogen, even though it's on the left side of the table with the metals, is considered a nonmetal. Metals tend to be solid at room temperature. They tend to be shiny. They conduct heat and electricity. And they are malleable. The nonmetals tend to be gases or solids at room temperature. The only exception to that is bromine, which is a liquid at room temperature. And then the metalloids have properties of both metals and nonmetals.